So Chris, with that, thanks again for joining us and take it away.
Great, thanks a lot, Maria. And thanks for the opportunity to be here, talk with you. As Maria said, I taught for 25 years, so it's great to be back with a number of students today. And I hope that, I hope that today can be a conversation. I do have a lot of slides, but don't hesitate to stop me if you have a question about something I'm saying. I know that you all are coming at this mostly from a very different perspective. As Maria said, my background is in physics and astronomy. I got my degrees in physics. I did my research in radio astronomy, and my work is in the field of high mass star formation. I'm not going to talk about that stuff today because I really want to kind of give you an overview of this very particular use of the radio frequencies of the spectrum, of the electromagnetic spectrum. So the telescopes you see here are the telescopes of the Very Large Array, the Jansky Very Large Array out of Socorro, New Mexico. If you ever get a chance to go visit, I highly recommend it. It's an amazing place. I'll talk a little bit about some of the science that's done here. I'll start, with an overview. Here's kind of what we're going to talk about today. And by the way, I taught for enough years to know that an hour and a half is a very long time to sit and listen. So again, stop me, ask questions. At a few points, I'll ask you questions. But I think, the human brain at around an hour kind of saturates, right? And you're done with intaking information. So I will try to make sure that we have a chance to kind of have some back and forth during all this. So I want to start with motivation, sort of why astronomy and radio astronomy in particular are important and worthy undertakings. I want to talk about some astronomical uses of the radio spectrum. Mostly when people think of radio astronomy, they think of sort of just receivers, right? Passive use, you have radio waves coming in and you translate those into images, spectra, other ways to understand the universe. But radar imaging is also another use of radio waves, right? You actually send out radio pulses and receive the reflected radio waves back, and those allow you to also make images. That's more active use of the spectrum. I want to talk a little bit about the radio spectrum and a brief history of radio astronomy, which has its origins in some places you may not expect. Talk about types of radio frequency radiation and kind of unique benefits of using radio waves to study the universe. And then we'll get into some details, talk a little bit about how a radio telescope works, various pieces and parts of a radio telescope, which, look a lot like the satellite radio dishes. In fact, a little story I'll tell you, since I've shown you a picture of the Very Large Array. When I was a graduate student, the year before, I went out to Socorro to spend the summer there. The tradition was, and you may have done this in various modes, was to have a prank. Right? And so the prank that the summer students, who were all undergraduates, did that summer was they sold the Very Large Array in a classified ad. So back in the day, there were physical newspapers that you held in your hands, and they had a classified section, which would have for sale. So the classified ad said, for sale, 27 25-meter dishes, $200 for best offer, HBO, you bet, right? So it was, and then the phone number was the phone number of the director of the BLA at that time, who was Miller Goss. And he started getting phone calls. One guy was like, I want one for sure, maybe two. Do I need a trailer? I mean, these things are 25 meters across, right? So they're very, very large. Anyway, all that to say that I'm going to tell you a little bit about the elements of radio telescopes and to talk a little bit about some of the NRAO radio telescopes and how they function, the kinds of science that they can do. And I've got a lot of slides of just some nice pictures of radio astronomy observations that hopefully we can have some back and forth about. And then where I want to end is sort of what I'm doing currently, which is talking a little bit about protecting the radio spectrum, right? Because all the things that we'll talk about today are dependent on being able to see them. And one thing I want to emphasize is that radio telescopes are looking at very, very faint signals, right? And so, sometimes these things are hundreds of decibels below where commercial transmitters are functioning and commercial receivers, right? And so if those types of uses of the spectrum dominate, then the very, very faint things that the universe has to reveal to us are completely washed out. And so if we are able to protect the radio spectrum, we can actually still continue this field of study. And that's really important to me. And I hope it'll be important to you too. And the thing I want to talk about is something that we're working on now called operational data sharing, which is a creative way to use the radio spectrum sort of side by side and in cooperation with active users of the spectrum. And then we'll have some time to chat at the end. So why care about radio astronomy? Well, I mean, it's really old, right? Astronomy, pretty much all cultures around the planet have always looked at the night sky. And they've looked at the beginning with their eyes, and then early on they started making measuring instruments. And I'm not going to go into the whole history of astronomy, right? Because that's a very, very long discussion. But I just want to emphasize the fact that cultures around the globe have been interested in astronomy for a long time, because we live on a planet that's not enshrouded with clouds, and we can actually see the night sky. And that drew our eyes up. It allowed us to think about, why are these things moving the way they are, right? Why do the stars rise in the east and set in the west in the course of the night? Why does the sun do the same thing, but at a different rate, right? There are all these clues about how the physical universe works. And astronomy really opened our eyes to a lot of those things. Astronomy also kind of forced humanity to develop different types of mathematics, algebra, calculus, right? To kind of to engage with these motions in the sky that on the face of it make it look like we're in the center of the universe. But in reality, what's been revealed over time is that we're located in a small corner of one galaxy that's ones of billions of galaxies spread out through the universe. And what the night sky kind of presents to us is this unbelievable and unique cosmic laboratory, right? There are things going on in the universe that we can't simulate, right? We have yet to build a successful fusion reactor. There's a great fusion reactor at the center of the solar system, right? In the form of the sun. And the galaxy is riddled with billions of these fusion reactors doing things that we can't do. But we can observe them, right? We can receive the radiation from all these things. And in getting that radiation, we can start to think about the physics behind all of these processes. And in doing that, right, in trying to figure out what's going on in the universe, humanity has developed some incredible technologies, right? And radio astronomy is a small part of that. But a lot of the elements, for example, in your cell phones, right, were developed for use in radio transmission and reception. And a lot of the very sensitive receivers and transmitters and technologies and electronics that are in all the modern technologies that we all use today, many of them had their origins in radio astronomy. So how do we get information from the universe, right? If we're going to use this information to figure out what's going on, how do we get it? Well, we get it from radiation, largely, right? Optical, infrared, radio coming at us from the sky. Our eyes are sensitive to a very narrow portion of the spectrum, but then all this technology that we've developed allows us to see a much, much larger picture of the universe. Pretty minimal, but particles, right? Things come at us from the universe, right? Asteroids crash down and enter the atmosphere and come down to the surface of the Earth. That gives us clues as to what's going on. And that's very unique, right? We have very little stuff coming at us from the universe. And when we get those things, we can study them. They tell us about the history, at least of the early solar system. And then more recently, gravity waves, right? You might have heard of LIGO. You might have heard of a project called Nanograv. And these are ways in which we can actually see how waves in the universe, gravity waves, tell us about the evolution, especially the very early universe. Because as it turns out, and we'll end on this slide at the very end, when you look out into the universe, there is a moment where the universe sort of clears and you can actually see what's going on, right? And that's when electrons and protons hold on to each other and the universe kind of clears. That's the moment from where we receive the cosmic microwave background, right? So that's the first moment we can actually see stuff, we can see radiation moving through the universe. But earlier than that, it's like there's a shroud and we can't see any earlier than that. It's around 300,000 years after the Big Bang. So in order to explore those earlier times in the universe, there are other ways, one of which is gravity waves. So when we use radio astronomy when we use the radio spectrum to carry out astronomical observations, we are really looking to detect very, very faint radio waves from space. There are cases more recently of using radar for imaging. So the image you see here is actually a radar image that was made using the Green Bank telescope, which I'll tell you a bit about, and then the Very Long Baseline Array as receivers. So basically the GBT is the transmitter, the VLBA are the receivers, and we've been able to reconstruct some pretty fabulous images of the surface of the moon. It turns out that very, very little of the radio spectrum that you've heard a lot about and know a lot about is actually protected for radio astronomy. So there are international rules and there are sort of national level rules. So there's something called the International Telecommunications Union, the ITU, where countries from around the world come together to sort of say, yes, we think this is how the radio spectrum should be used. And then those rules, which are set every 4 years at something called the World Radio Congress, those go to the national level, and then they're sort of implemented at the national level. So you might have heard of the NTIA, which manages spectrum for government uses, like military, for example, and then the FCC, which governs commercial uses. But the thing that I want to emphasize here is that below 100 gigahertz, there's really only a few % of the radio spectrum that is preserved. And this is too small to see anything, but I just want to emphasize. So this goes from low frequencies to high frequencies. And you may not be able to see here, but this is 3 megahertz, 30 megahertz, 300 megahertz, 3 gigahertz, 300 gigahertz. So these are sort of logarithmic steps going up in frequency. And there are some of these little narrow yellow bands are what is actually designated, protected, either fully or partially for radio astronomy. So it's a very small fraction of the spectrum that radio astronomy doesn't have to worry about other things, right? But in most of the spectrum, it's allocated to government use or to commercial use, all of which is important. And you've been hearing about and know about all of the amazing uses of the radio spectrum. One of those amazing uses of the radio spectrum is radio astronomy. So, a brief history. So here's the electromagnetic spectrum. This is a plot that you've seen in various forms all the time, I'm sure. But basically on the left there, going from bottom to top is wavelength. And then from top to bottom is frequency. Of course, those are inverse, right? High frequency are short wavelengths. So the part of the spectrum that our ancestors looked up at the sky with is this very narrow part of the spectrum that is the optical part of the spectrum. Why are our eyes sensitive in that part of the spectrum? Any ideas? Just coincidence? Why that little narrow part, would you think? Yeah.
Is that maybe the most common band of light from the sun?
Perfect. Yeah, great answer, right? So
there's one more guess here in Albany. That was your guess? All right, second that.
Yeah, so with the same guess, yes. So in fact, if you plot the spectrum of the sun, it peaks right very close to where the human eye responds, right? And so living things on the surface of the earth, I mean, some of them kind of go into the infrared, some of them go into the ultraviolet. Insects and things have different reasons to have a little bit broader, but exactly right. We evolved in an environment where we were illuminated by the sun's light, and that's where the solar radiation peaks. Other parts of the spectrum you've probably heard about at shorter wavelengths, ultraviolet, X-rays, and gamma rays. These are high frequencies, right? High energies. And these are the things that make superheroes, right? You need those wavelengths to create superheroes. You never hear of, Radio Man, right? Those are low frequency, low energy waves. But radio, TV, right? The things that sort of we coexist with and depend on all the time, right? You hop in your car, you turn on the radio, there you go. You are getting those long wavelengths. So in this part of the spectrum is where radio astronomy functions. So The history of radio astronomy, or the ability to sort of generate and receive radio waves, starts in the late 19th century, almost 150 years ago. Heinrich Hertz, you may recognize that last name for our unit of frequency. So what's shown here is just a sort of early engineering schematic drawing of an early transmitter and receiver, radio transmitter and receiver. And so once humans kind of figured out how electromagnetic radiation works, right, with perpendicular electric and magnetic fields, then it was determined there were ways to sort of artificially generate these types of waves. And coming back to your answer to the question, right, I'm sort of seeding the answer here. What's the most obvious optical astronomical source in the sky?
Is what you think.
The sun, right? I mean, you look up at the sky, we can't even look at stars with our eyes during the day because the sun is there, because it's not a particularly, intrinsically bright star. It's sort of an ordinary star, but it's so darn close that all the other stars fade in comparison, right? So when the sun is in the sky, that is the brightest optical source in the sky. When that source sets, then all the other optical sources reveal themselves. We see we see the stars. The moon is pretty bright. You can see the moon during the day. My wife said her grandfather used to tell her that if you can see the moon during the day, that means you're lazy. So he would always deny it. Cheryl would be like, "Look, Grandpa, there's the moon." He's like, "I don't see it." So probably no surprise that when these early investigations of radio waves started to happen, people started to look for the sun, right? They said, okay, it's the brightest source in the sky. Let's go find the sun with radio waves. Nobody could do it. And they didn't know why at first. We'll kind of come to that in a little bit. But names you've probably heard of, like Edison, and names you probably haven't, like Wilson and Shiner, tried to look for radio waves from the sun, and they were unsuccessful. They developed all sorts of different kinds of experiments to look for radiation from the sun. And there's kind of an analogy to this in ancient times. So you probably, you understand basically the heliocentric view of the solar system, right? You've got the sun at the middle and you've got the Earth going around. And as the Earth goes around the sun, it turns out that nearby stars move in parallax a little bit, right? When you're on one side of the sun and then you go to the other side of the sun, stars tend to go back and forth. You can do this, here, hold your finger out in front and look with one eye and then the other. What does your finger do?
Move.
It pops back and forth, right? So here's the Earth on one side of the sun, here's the Earth on the other side of the sun, and that's a nearby star. And the wall is the distant stars. So parallax is that effect, right? Your finger moving back and forth. So Greek astronomers, a long time ago, proposed maybe the Earth moves around the sun. If the Earth moves around the sun, we should see parallax. We don't see parallax. Therefore, the Earth doesn't move around the sun. Turns out the parallax is very, very small. And it's so small that what do you think you need to see it? You got to have a telescope, right? The human eye doesn't have enough resolution to see the parallax of nearby stars, even the very closest stars. So just because you can't see something doesn't mean it's not there, right? So the idea was there, right? That the Earth moves around the sun, but until observation shows it, well, the telescope didn't come along until 1609, right? Galileo built that first telescope. As soon as the first telescopes were operational in the early 17th century, guess what was discovered? Parallax. And then that whole idea, right, that you have a heliocentric solar system made more sense. So just because they couldn't see radiation, radio waves from the sun, doesn't mean they weren't there. They just didn't have a sensitive enough instrument to see it, right? They had good ideas, they had good proposals, they weren't amplifying the signal enough. Amplifiers didn't exist, right? I mean, there were technologies that weren't there that meant that these experiments couldn't happen. There was another famous name. You may have heard of Planck, like Planck's constant. It's very useful in physics. He estimated that solar radiation should be a fairly small thing, right? That it was it had a low value, at least at wavelengths that could be detected. So there was a flurry of activity, like in the late 1880s and 1890s and up to about 1900, and no one saw radiation from the sun. So efforts stopped. People just kind of like, okay, I guess there's no radiation from the sun, which is understandable, right? It was a busy time. World War I happened, right? And all these other things were happening in the world. But solar radiation, right? The early attempts to detect the sun failed. Well, along comes a person named Carl Jansky. Now, Carl Jansky was working as an engineer, and in fact was working on the advent of transatlantic radio phone calls, right? So the attempts to sort of transmit radio waves across the Atlantic so you could have communication across the Atlantic Ocean. And in some of his early work, he detected that they were detecting interference at long wavelengths, 15 to 30 meters. And he was a Bell Labs engineer. Now, and you may well wonder why there's a baseball cap there. Well, there's two reasons. One of which is the National Radio Astronomy Observatory softball team based here in Charlottesville. We are the Janskys. That is the name of our softball team. And you may notice instead of a number on the hat, we have 10 to the minus 26. Any idea why we would have such a weird number on there? It's a unit of flux density for radio waves, which we call the Jansky. So the unit of flux density that we use is watts per square meter per hertz. So 1 watt per square meter per hertz is 10 to the minus 26 watts per square meter per hertz is 1 Jansky. So the units that radio astronomers use for flux density, a Jansky is actually a fairly powerful radio source, right? Radio telescopes are functioning down at the micro-Jansky level now, right? In fairly short observations. So 1 Jansky, 10 to the minus 26 watts per square meter per hertz. What that means is that sort of starts to give you an idea of the levels at which radio telescopes are detecting things, right? Way below the noise floor of commercial transmitters and receivers. He built an antenna that functioned at around 150 megahertz. This is a frequency band that's used actually all the time now. VHF, right? VHF frequencies. It's used for emergency services. It's used for a lot of other transmissions. And he built this. You can kind of see the wheels there, and you can imagine, this sort of architecture for a radio telescope is still utilized, right? The Green Bank telescope rotates around on a circular track with enormous wheels, right? So basically, if you want to point a radio telescope, either oriented at a different angle or pointed at a different place in the sky, you have to have 2 axes, right? And so radio telescopes, like commercial satellite dishes, have 2 axes of motion, right? They have azimuth and elevation. And so this is one of the first radio telescopes. This is really the first functional radio telescope built by Carl Jansky. And in 1932, during the Depression, there was this announcement thank you. Thanks. There was this announcement in the New York Times that said, new radio waves traced to the center of the Milky Way galaxy. Mysterious static reported by Carl Jansky, held to differ from cosmic rays, direction is unchanging. So what he was able to detect with that first radio telescope were some fairly bright things nearby and distant thunderstorms. But behind all that, there was this sort of faint hiss that was seen in many portions of the sky. And actually, there were a few bright spots in it that appeared to move, but they didn't move with the sun, they moved with the stars. So it was what's called sidereal motion, right? So sidereal motion means, remember we talked about that before, there's the fact that the stars rise and set, and then there's the sun, which apparently rises and sets, which is actually us orbiting the sun. But those two things are called stars, sidereal motion, and the sun is stellar motion. So the emission that was detected by Jansky was sidereal, not solar. What he was really detecting for the very first time was the plane of the Milky Way galaxy. right? It turns out that the Milky Way galaxy actually was emitting quite strong radio waves, right? And some of the brightest radio sources in the sky are actually quite distant sources that are emitting radiation in very different ways that we'll talk a little bit about. So this was May 5th, 1933. And he was actually very interested in continuing with these experiments, but Bell Labs had other projects they were interested in and working on, and they were a commercial company. They needed to make money, right? And so radio astronomy was not at the time generating a lot of funds for Bell Labs. And so he was not able to do any more work, unfortunately. He did go on to a career in radio astronomy later. So skip forward about 5 years. We're now in 1937, and a person named Grote Reber built in Illinois. Actually, I think it was his mother's backyard. I don't think it was his backyard. It was his mother's backyard. He built the first parabolic radio telescope. It was pretty large. It was 10-meter diameter telescope, right? So bigger than a sort of satellite dish that you see sitting in a field somewhere. And there's actually, I say replica here. It's not really a replica. It's a kind of a restoration, right? It needed major work. So I think a lot of the structural pieces have been replaced. But it's actually, his actual telescope was moved to Green Bank in the 50s and has been there since. And what he was able to do was to actually make some of, to move from simply detecting radio waves from the universe, he was able to move to actually start to identify some of the sources in this region. So you can kind of see that arc across the sky. That's a contour map, right? So like if you've gone hiking, topographical map, right? You've got contours, the highest contours are the brightest radio sources. And that contour map is, again, similar frequencies to what Carl Jansky was making observations, 160 megahertz. And what you see here, this is a publication from, you can see there, 1944. So this is actually during World War II. And there's Grote Reber a little bit later in the 70s. And so what we now know he was detecting in this image was actually the galactic center, right? So there's the first image of the center of the Milky Way galaxy. At this time, it had been recognized by astronomers that the Milky Way, that all these things in the sky that were called spiral nebulae, there was a big debate that happened, right, in the 20s about whether these things were nearby or very, very distant. And it was figured out that, oh, in fact, they're very distant. The universe is much bigger than we thought. But this is the center of our galaxy, right, where we live. And it's in the constellation Sagittarius. Located in the constellation Cygnus. It actually turned out, it wasn't known at the time, it was another bright radio source. It turns out to be a radio galaxy, a fairly famous radio galaxy. And then there was another object, which was actually in the galaxy, which is a supernova remnant in the constellation Cassiopeia. So you might notice something interesting here, which is, by the way, that optical astronomers first identified the stars in the sky, right? Greek, Roman, and Persian astronomers first identified and named many of the stars, right? A lot of stars have very ancient names. And then those stars were grouped by different cultures into constellations. And now those constellation names happen to be in parts of the sky where we have radio sources. So we actually have, Cassiopeia A, which is the brightest radio source in the constellation Cassiopeia. And so we actually still kind of pull along that, we started by saying this is a very ancient cultural practice. We pull along those very ancient names, even into the most recently discovered objects. All right, so now we're in the 40s. World War II starts to happen. And for various reasons, which let's talk about for a moment, large resources were put into radar technology, radio, all over the world. Why would that, think about what was going on in World War II. Think of the state of technology. Why would people have cared about radio waves and radar in the 1940s?
Detect planes.
Detect planes, right? Very good.
Send messages long range.
Send messages long range, good. And someone here said communications, right? Yes.
Detecting submarines?
I'm sorry?
Detecting submarines like U-boats?
Yes, detecting, right, all sorts of detection, right? So that may have been more sonar, but still, same idea, right? So actually what you start to see in the 1940s are some of the uses of the radio spectrum that you all are more familiar with, right, than radio astronomy. So just pointing out, radio astronomy came first, not really, but all of these incredible uses, right? So you have communications, you have detecting planes. Do you know any famous examples of the use of radar in World War II?
Yeah, I think the British used it to win the Battle of Britain.
Very good. The British used it to win the Battle of Britain. So in England, right, they used some of the first radar to send out radio pulses that would then reflect back off incoming bombers or fighters, and they would be able to scramble their own fighters in the right direction, right? Instead of scanning, you know, the entire southern sky of England and sending planes out on sorties in various directions, they knew exactly where to go. So that was critically important. And an interesting historical note in World War II is that Australia and England in particular were sort of given the task of radio astronomy, radio communications, use of radio waves during World War II. And America famously took on the Manhattan Project, which was the nuclear bomb project, right? So there were big resources put into these two areas. And as a result, right, you end World War II with all of these highly trained radio engineers with some work for them to all do, but also a lot of new applications that started to develop. So the really kind of explosion of radio astronomy as a form of astronomical pursuit really gained a lot of speed after the war. An astronomer named James Stanley Hay discovered radio emission from the sun, first time, right? Finally happened, right? We had had sensitive enough receivers to finally see it from the sun, and actually sort of detected the fact that that the radio galaxy in Cygnus that was first seen in Groth-Reber's image, right? That contour image, that was actually a radio galaxy. So it started to be recognized that objects like galaxies, which were now known to be outside of our own Milky Way, had their own type of radiation that could be detected via radio telescopes. So it led to this big explosion in the understanding of the value of radio waves for astronomy. So after the war, the UK, Australia, and Netherlands in particular moved a lot of their expertise that they had developed in World War II, that got kind of moved into radio astronomy. All right. This is one example, sea interferometry. Okay, so we're going to talk a little bit later about the different types of radio telescopes you can build. One way to get a more precise bearing on a source of radiation is by using what's called sea interferometry. So you have some radio waves that are coming straight into that receiver that's on the cliffside. And then you have other radio waves that reflect off the surface and then hit the antenna. So those two waves get combined, and combining waves is a type of interferometry where you form an image where you at least find the position of a source more precisely. An interferometer allows you to do that. And so this was actually developed. This is one of these techniques that was developed during the war that then got built into some astronomical uses after the war. And then finally, the technique of interferometry itself started to grow, and you have the advent of the first interferometers in England. Here's an example of sort of where radio astronomy technology was after the war, right? So this is a telescope that was built in 1957, the Lovell telescope at Jodrell Bank. Anyone know where Jodrell Bank is? Yes, Sonia.
Outside Manchester.
Yes, so it's in the UK.
And they are actually
Yeah.
not Photoshop.
Yeah, I think there are, is there a fence there on the base? Oh,
Yeah. And now a brand new.
Right, yeah. So, I mean, radio telescopes, and I'm just going to take a little aside here to point out the fact that radio telescopes are often built in very rural locations. Why would you think? Why would you want to build a telescope in a rural location?
So interference from other devices doesn't mess with the telescope.
Yes, interference from other devices is not as big of a problem. Excellent, okay?
You get seconds for research.
That's exactly right. So in fact, this is kind of going to lead us to where we're going to end up today, right? which is that when radio astronomy was getting started, it was possible to isolate oneself from sources of radio frequency interference, right? You could build telescopes out in the country in England. You could build telescopes eventually out in the plains of San Augustine in New Mexico. And you were pretty much out of the reach of most forms of RFI. You know, a plane would fly over occasionally. Maybe you would see radar from a near airport, but you really could isolate yourselves. And this is an example, right, of picking a location that was far away from sources of RFI. But then what happens in the intervening years is, especially with the advent of cell phones and cell phone towers, even remote locations start to have fairly powerful sources of radio waves located pretty near to them. And then eventually you get to the place where the sky is full of sources of radio frequency interference, right? You have constellations like Starlink, where you now have, how many is it, Blake? 8,000?
As of June, it was 7,800.
7,800, right? So you have 7,800 sources of radiation that don't care how remote you are, right? They're in space and they're in low Earth orbit. And so they are sort of tracing over wherever you are, whether you're in rural England, whether you're out in the plains of San Augustine, whether you're out in Chile, in the high plains of Chile at the Alma telescope. So you could get away from radio frequency interference in the 50s. You can't get away from it now. And so that's one of the big challenges, right, to radio astronomy. And one of the real needs that radio astronomy has to have cooperative agreements and coexistence with a lot of these types of radio transmitters so that we can still keep doing the science that we so love. It's beeping back to me like it doesn't want to go forward. Oh, okay, now it's going to go forward 10 slides. Okay, so let's talk a little bit about types of radiation and some of the unique benefits of using radio frequency observations. So what are the astrophysical processes that give rise to radio waves from sources, right? Because remember I said at the beginning that radio astronomy is this sort of cosmic laboratory. Well, in order to be a comprehensible cosmic laboratory, we have to understand what processes give rise to these types of radiation. So basically, if you have a charged particle, if you have an electron and it moves in a curved path or in a straight path and is accelerating or decelerating, it's going to radiate, right? And so anything that you can do to change the path of an electron is going to make it radiate. Well, two things very clearly change the path of an electron. One is magnetic fields. And you may have seen this in the physics class, right? If you have an electron in a magnetic field, it spirals around that magnetic field and it'll sort of propagate along the field line. And what happens as it spirals around that magnetic field is that it gives off radiation in all directions, right? No matter where you are around that magnetic field line, you'll see the radiation coming off. That's what we call synchrotron radiation. That comes from charged particles, could be a proton too, moving along magnetic field lines. The second way is thermal emission, okay? And thermal, you can imagine a plasma, right, which is made up of, free electrons and protons. Well, the electrons are going to see those protons and they're also going to, maybe they'll get captured, right, and they'll start orbiting the proton, or maybe they'll just kind of skim on past. But if they're close enough, they're also going to have their path changed by the presence of that charged particle. That'll give rise to thermal emission. That's dependent on the temperature of the plasma. And, what's the requirement for thermal radiation is that you have ionized charged particles, right? They have to be in a plasma. So those both give rise to what we call continuum emission. So that we see sort of across the radio spectrum. And then there's also spectral line emission, right? These are, this is emission that's associated with particular unique spectral lines. And there's one very famous spectral line. Has anyone ever heard of the H1 line, the line of neutral hydrogen? Like, do you know what that arises from? Do you know the physics behind that? Sorry to put you on the spot. But you've heard of it. You've heard of the 21 centimeter line.
I know what frequency it is.
That's right. Okay. You want to share that?
It's 1420 megahertz.
1420 megahertz, right? And in fact, remember that chart I showed you at the beginning with all those little tiny little slivers and protected parts of the spectrum? One of the tiny little slivers is 1420 to 1427 megahertz, which is the part of the spectrum where the H1 line is. Okay, so the H1 line arises when you have a proton and an electron. And particles have a characteristic called spin, and the spins can either be aligned or anti-aligned. And when the spins are aligned, the hydrogen atom, right, because a proton and electron is just a hydrogen atom. When the spins are aligned, that's a slightly higher energy state than when they're anti-aligned. And on some known, at some known rate, if you have the spins aligned, they will eventually spontaneously anti-align. And when that happens, you give off a 1420 megahertz photon that comes off of that hydrogen atom. Well, good for us, the universe is chock full of hydrogen, right? Hydrogen is everywhere, right? It's the first element on the periodic table. It's throughout the plane of the Milky Way galaxy. It's in extragalactic sources. So if you can successfully detect H1, you can see the structure of the Milky Way. You can, and it's a line, so it carries a ton of information, right? It carries information about the temperature of the gas. It carries temperature about what else might it carry? What does a spectral line give you that could be really kind of cool and interesting?
Direction if it's red or blue shifted.
Excellent. Direction of it, and if it's red or blue shifted. So is it moving towards you or away from you, right? So if you think about it, right, if you have a spectral line, it can have a Doppler shift. And so if you're looking at a part of the galaxy where one of the arms of the Milky Way is moving towards you, it'll be a blue shifted cloud. It's moving away from you, it's red shifted. So it's one of the few ways, I mean, there are other ways, but it's a really critical way that we can detect motions of things, right? So we can detect in extragalactic sources, we can detect motions in rotations of disks in other galaxies. And in fact, H1, the rotation of H1 in galaxies is the reason we think that there's this stuff called dark matter, right? Because we can see from the rotation curves of galaxies that come from the H1, that, as you'll see in a moment, is much more extended than the optical extent of the emission coming from stars, that galaxies are spinning at a rate that implies there's much more mass there than we see visually. So thus the presence of dark matter. Okay, so just a couple visuals. There's what I was trying to do with my hands and fingers. There's a charged particle rotating around a magnetic field, giving off radio waves. The other cool thing is you can actually get what's called polarization. So if you detect, radio telescopes not only detect brightness, but also the polarization direction, you can actually get, you can actually understand what the direction of the magnetic fields are in your source, right? So I want to pause for a minute and emphasize, right? One of the miraculous things about all sorts of radio astronomy is that without going there, which we will never do to some of these places that are, you know, millions of light years, hundreds of millions of light years away, without going there, we can say what elements are contained there. How are those elements moving? What are the magnetic field strengths? What are the magnetic field strengths, you know, orientations? We can tell so much about the physical nature of these sources without ever going there, just by sitting there with the big radio dish and receiving photons. But we have to protect the radio spectrum to be able to receive those photons, right? Otherwise, it's all cat videos, right? That's what we need to preserve, right? Whether in time or in frequency, we need to preserve parts of the radio spectrum so we can continue doing this important work. Thermal emission from the radio. This is emission from, you know, objects that have some temperature. You've probably seen this in other contexts referred to as black body radiation, right? So it turns out that objects that have temperatures sort of in the low kelvins, right? 0 Kelvin is absolute zero, but 3 to 30 Kelvin, those give off strongly in the millimeter and submillimeter. And it turns out, we'll get to some images in just a sec, that those wavelengths are a great way to study star formation, right? To look at the star formation. And at the bottom there is just an example of how a charged particle, an electron, actually can have its, you know, it accelerates because it's moving in a curved path. And any acceleration is going to cause some radiation to come off in the form of what's called bremsstrahlung or braking radiation. Oh, wait. What I want to show here, remember the guy I said who initially discovered that the sun did have radio waves coming off it? The reason why is that he was actually looking at the sun when it was in an active phase. So it actually had a lot of sunspots. And when it was in an active phase, it hiked the strength of the radiation. You can see that's a logarithmic plot there by a factor of about 1 million. So the sun becomes, at wavelengths where they actually had detectors, the sun suddenly became 1 million times brighter because of these sunspots. And they're like, oh, the sun does give off radiation. What they were trying to do before was detect stuff way down here. And here's our good old Carl Jansen, right? Watts per square meter per hertz. Notice where we are, 10 to the minus 24th. 100 Jansky source. That's a big source, but again, in terms of actual watts per square meter per hertz, incredibly small numbers. My battery might be going. Oh, maybe I have to point over there. Okay, so why observe with radio waves, right? We've talked about the history of radio astronomy. Well, radio waves not only make it possible to detect things that you can't get at other wavelengths, there's really no other way to observe neutral hydrogen. That's it, right? So if you lose that capability, you can't look at neutral hydrogen anymore. That's a big loss. But they also, radio waves do a very good job of traveling through dusty regions, right? It turns out that if you have stuff like in the plane of the you can see all across the Milky Way. You can see through the galactic center. You can see the other side of the galaxy. You can look through the plane of the galaxy at other galaxies. Whereas at optical wavelengths, right, you've got all this gas and dust in the plane of the Milky Way that optical light can't travel through, right? I mean, you've been out on a foggy day, right? And on a foggy day, have you ever been out and it's so foggy you can see like 20 feet? Right? That's because the optical photons are getting scattered by all that stuff, right? By all that water vapor in the air. So you actually can't see very far. But then you pop on your, infrared goggles, which are lower frequency, and you can, oh, there's someone about to kill me, right? So you can see if you're in a horror film. Then you can start to see people moving through the fog in scary ways. Okay, so and radio emission can give us a lot of information on the magnetic field strength, line of sight velocities, as you pointed out. And also, I pointed out at the very beginning, right? You can't use an optical telescope during the daytime. The sun is too bright, it dominates. Radio telescopes, especially at lower frequencies, can operate day and night, right? So the very large array operates throughout the day. Okay, so here we're going to get into some characteristics of radio telescopes. So first thing you have is the surface, right? So you have an aluminum reflecting surface that focuses incoming waves to what we call prime focus or subreflector. Okay, so the direction that you point the telescope in is the direction that you catch those radio waves from. And shown here is the Green Bank Telescope in West Virginia. The subreflector does one of two things. You can actually put a detector there, right? You can actually put a receiver right at the subreflector, or you reflect down into what's called the feed pedestal. And this is a VLBA antenna, very long baseline array antenna. These are the 25-meter diameter radio antennas. And you can actually rotate the subreflector to direct the radiation into one of a number of receivers that are in the feed pedestal. And here's an example of a feed pedestal. This is the VLBA shown here. And you can see there's a number of receivers there. And you can probably see all sorts of cool things that we don't have time to go into. But anyone have a guess what these little things are? Like there's one associated with each of these receivers. What do you think these little things do? I'll give you a hint. Think of weather.
Chris, which little things do you have a pointer on? Do you have a pointer on your slide that you can use?
Oh, yeah, sorry. I don't have a pointer that'll show up as a demonstration, but if you look at the 2 centimeter receiver, there's something that looks like a little stage light to the side.
Oh, stage light right next to it. Okay, what are those?
Any guesses? We can imagine these things are out in inclement weather. It gets cold, snow can fall, ice can form, right? So these are a way to get rid of snow and ice. These are little heaters, basically, right? These are ways to get rid of stuff that forms on the surface. And obviously, all of the receivers have to have covers, right? So those are sort of radome kind of covers that cover the receiver entrance. So for the VLBA, the subreflector can steer that beam, that incoming beam of radiation into any one of these receivers, depending on the particular science you want to do, right? If you want to look at H1, then you steer it to the 20 centimeter receiver. If you're interested in a particular spectral line that occurs in what's called Q band, which I think commercial is sometimes called V band, up in the 40 gigahertz range. Then you might direct towards the 7 millimeter receiver. Come on. So under the dish, right underneath those that feed pedestal, then you have the actual receivers, and this is just showing some of the electronics underneath the dish. And typically, a large telescope will have a receiver room, with a door. Open the door, you walk in, and when the telescope is stowed, that room makes sense. It's oriented properly. But as a telescope, you never want to be in there while the telescope's observing, because that whole room is tipping around as it points at the sky. My radio waves are not working well. Okay, so what sets the resolving power of a telescope is two things, right? The first thing is the wavelength you want to observe at. That's in the numerator, and the denominator is in the size of the dish. So it turns out, if you remember from the electromagnetic spectrum, radio waves are big, right? They are sort of centimeter, 10 centimeter, meter wavelengths. So they're much bigger than optical telescopes. So to have the same resolution as an optical telescope, radio telescopes have to be, you may have noticed, a lot bigger, right? So like the Jodrell-Bank telescope, built in the 50s, was much larger than any optical telescope that had been built at the time. So if you want to build a radio telescope that can observe at very high resolution, you've got to build a big telescope. And there's two ways to do this. You can either have a very big dish on the left. That's a single dish telescope. That's the Green Bank telescope in Green Bank, West Virginia. Or you can build an interferometer. Remember that seaside interferometer that was built on a cliff? Well, you don't necessarily have to reflect waves off the surface of the ocean, right? That has all sorts of issues. What if there's waves? What if there's a storm? It's not a very smooth surface. You build what's called an interferometer, right? And so you actually combine the radiation hitting a number of telescopes, and then the resolution of your telescope depends on the distance, the largest distance between any two elements in the interferometer. And that's how the Very Large Array, seen here out in the plains of San Agustin in New Mexico, can actually get very, very high resolution images. And again, the way an interferometer works is that every two antennas comprise what's called a baseline. And so if you have a large number of antennas, you have a large number of baselines, right? You can imagine you've got antenna 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to 6, all the way up to 1 to 27, and then 2 to 3, 2 to 4, 2 to 5, right? So there are hundreds of baselines. And it turns out that all those baselines go through what's called a correlator. Each baseline goes through a correlator that basically combines the signals from each of those antennas, and you get something called a visibility. And those visibilities are actually recording the interference pattern along a lot of different axes of the incoming radiation. And so the final step that you have to do as a radio astronomer is you have to Fourier transform that interference pattern to see what the actual image on the sky is.